Right, this is Karmel Shehadeh presenting our work on operating room to downstream elective surgery planning under uncertainty on behalf of my colleagues. In this paper, we propose a new combined elective surgery assignment and sequencing and scheduling problem called the ESASSP that involve multiple operating room and also in addition to that, their downstream recovery unit, intensive care and surgical ward. This problem is as follow. You have a master surgery schedule where surgeries, specialties are assigned to the operating room. You have a list of elective surgeries and you want to decide the assignment of these elective surgeries to OR, as you can see here, but not only the assignment, also you need to decide the sequence of start time in each OR for each surgery. These decisions are not taken only considering the capacity of the OR, but also the capacity of the downstream units where patients needs recovery after the surgery. Okay, this is a challenging optimization problem, in part because there is significant variability in duration and post-operative length of stay. To show you this variability, this is a result of analyzing 9 worth of data from our collaborating health system for the isolated CABG, and there is other type of surgeries in the paper. In addition to the apparent variability, we noticed that the chi-square tests have rejected all parametric models to fit this data, indicating uncertainty in distribution type. So uncertainty plus combining assignment, sequencing, and scheduling leads to a stochastic and complex combinatorial optimization problem. To address this problem, we propose the first computationally efficient stochastic optimization model. I'm not going to go into the math because of this is a flash talk, but we propose a new stochastic program to address problem instances where we know the distribution for uncertainty, new distribution robust optimization model to address ambiguous distribution. We propose new and innovative reformulation technique to turn this to linear model, and also a column and constraint generation method to solve it. We also propose to address symmetry. We propose new symmetry breaking constraints and valid inequality to improve the computational performance of both models. We are lucky to have real surgery data from our collaborating health system and other health system to illustrate the potential impact in practice. Some of the results I will present shortly. First, you might ask what's the surgery volume suggested by each model, meaning the number of surgeries scheduled. This is a couple of instances from the model from different data sets. You can see the details in the paper, but the key insights here, it's obvious that the DRO model in red always suggests scheduling a lower surgery volume than the SP model. And I will show you the impact of that shortly. But before that, not only there's a differences in the scheduled surgery volume, as you can see in some of the instances, the DRO model tend to schedule more surgery at the beginning of the week and then fewer surgeries toward the end of the week. And this, as I will show you shortly, will lead to less congestion in the downstream unit. To show you that, we take this solution and we simulate them. This is results for one of the instances. The capacity of the downstream units are 10 during the week and 7 beds on the weekend. It's clear that the SP model here in blue, in most of the days, if we adapt such solution, we need more beds to accommodate scheduled patients, but the DRO model respects the capacity in all of the days, which is good because it's less congestion and we don't need to increase the capacity. Okay, to further analyze the impact on the downstream, we'll propose new metrics called the probability of exceedance, which is the probability that the number of beds needed on a given day exceed the capacity, and the mean exceedance, which is the average number of beds needed above the capacity on day T. As you can see here in the bar, which is the mean exceedance, and this is the probability of exceedance. In blue, the SP model always has a significantly larger probability of exceedance and mean exceedance for both the ward and ICU bed, indicating that if we implement solutions from the SP models, we will always require a larger number of beds than the capacity of the downstream unit, which is not good, but the DRO model respects the capacity. What happens if we adapt solutions from existing model, which is this is a typical multiple operating room that ignore the capacity of the downstream units when we schedule patients? We notice that this is example of the DRO model, but the insights from the SP are the same. Here in gray, you can see that if we ignore the downstream capacity, of course, we will schedule larger number of surgeries because we think that we can accommodate them. But in reality, as you can see here, the analysis of the probability of exceedance and mean exceedance of the capacity when we adapt solutions from models that ignore the downstream capacity and schedule a larger number of surgery. The probability of exceedance and the mean exceedance are significantly larger, meaning that we always violate the capacity of the downstream unit if we adapt such solutions. So hopefully this motivates you for the importance of including the capacity constraints of the downstream unit. There is also models that only assign surgeries to OR, but ignore the capacity, ignore the sequencing and scheduling problem. To show you the impact of ignoring the scheduling problem, here is one of the results. In gray, you can see that if we adapt solutions from model that ignore the scheduling problem, this leads to a significant delay in the operating room, and this observes for both DRO and SP. So this should motivate you for the importance of integrating also the scheduling problem in addition of the downstream unit. I don't have time to present a lot of results, but there are extensive results that show the performance of both model solutions under different distributions and their impact on these resources. We also have a detailed analysis of the CPU time of the model. The key insights that the DRO model has a better computational performance than the SVM model, and we also show the size and characteristic of problem instances that both can solve, in addition to showing the computational efficiency of the proposed valid inequality and symmetric breaking constraint. I hope you will look into these results in the paper, and I will look forward to present more on the informs and seeing you all. If you have questions, you can always email me at my email address here. And thank you for listening.